Welcome everyone. This episode is about sets. Let's start with a practical example where we use set operations. Suppose we have an image showing 3 sheep and a dog. Your task is to group these elements. To do this, you first need to recognize what animals are in the image and then determine where they are located. In the image, each pixel belongs to a specific object or the background. If you want to separate the individual animals, you can create a set for each animal containing the pixels that belongs to it. Now, let's start playing with set operations. If you want to see only the 3 sheep, you can group them into a set and discard the other pixels. If you want to extract all the animals from the image, you can enclose them in a single set. If you only need the dog, you can select its corresponding set. Thus, set operations allow you to easily isolate or combine different parts of the image. Let's dive into set theory. What do we mean by a set? A set is a well-defined collection of distinct elements. The elements can be numbers, people, animals, words, other sets, and many more things. In mathematics, the elements of a set are often written within curly brackets. Let's look at an example. The elements of set A are 1, 2, 3, 4, and 5. What happens if a set has no elements? Sets that have no elements are called empty sets. In this case, we write nothing between the curly brackets, or we place a crossed out zero inside the brackets. Let's continue exploring. Let's look at 2 sets, which we call set A and set B. The elements of set A are 1, 2, 3, 4, and 5. The elements of set B are the even numbers, which are 2 and 4. Every element of set B are be found in set A. We can call set B a subset of set A. This means that whatever belongs to set B also belongs to set A. The subset relationship is represented by a rotated U symbol with an equal sign underneath. However, set B is also called a proper subset because set A has an element that are not in set B. These elements are 1, 3, and 5. So a proper subset can never be exactly the same as the original set. The symbol for a proper subset is a rotated U without the equal sign. And with that, we have familiarized ourselves with the concept of subsets. Let's move on to set operations. Initially, let's have 2 sets, which we call set A and set B. Both sets contain elements. The common elements which belong to both sets can be classified into the intersection of the 2 sets, which we call the intersection of set A and set B. In mathematics, the intersection is typically represented by an upside-down U symbol. Union is another important set operation in mathematics. The union means that we combine all the elements of 2 sets into a common set, regardless of which original set they belong to. The union therefore includes all the elements that are in at least one of the sets. For example, the name European Union was chosen for a reason. Think of the individual countries as separate sets. When someone asked in Germany if they live in the European Union and their country or set is a member of the Union, they will answer yes. Similarly, if a French person were asked, their answer would be the same because their country is also part of the Union. In summary, the Union is a set that contains all elements from the given sets, so you will definitely be included if you were in any of the original sets. Another very important operation between sets is the complement, or the complementary set. If we have a set A, the complement is simply the part that lies outside of set A. Let's create a truth table. In the table, 1 represents true and 0 represents false. We can also think of set operation this way. Let's look at this in terms of negation. If we are inside set A, meaning A is true, which is represented by a value of 1, then the complement will be considered this region as false or 0. It will not select any element from here. Once we move to the area outside of set A, where A is false, the complement will be true because this is exactly the area it was interested in. Let's look at a practical example. My statement is that Berlin is not the capital of the country. Which countries will this apply to? Exactly every country except Germany. Let Germany be set A. So if I say Germany, the statement is false. But if I say not Germany, the statement is true. This is how the complement operation works. Let's revisit the union. The union can also be understood as the logical OR. We say the union of A or B. Let's look at the truth table. Let's take a real-life example. A little child asks their mother for ice cream and says, "Mom, get me vanilla or chocolate ice cream." The mother has the following options. If she doesn't buy either chocolate or vanilla, the child will be sad because the request wasn't fulfilled. If the mother buys a scoop of chocolate, the child will be happy because their request was fulfilled. If she buys a scoop of vanilla, the child will also be happy. But the mother can decide to buy a double scoop, one vanilla and one chocolate. In this case, the child will also be happy because the wish was fulfilled. So the OR operation results in true. The union can also be seen as an addition operation. Let's look at the example highlighted by the arrow. If A is false, 0 in the table and B is true, 1, then the union is equal to A plus B, that is 0 plus 1 equals 1. Think about the other cases as well. I would like to point out that adding one true statement to another true statement still results in a true statement. So think of it as an addition operation. Let's look at the intersection. The intersection can also be understood as the logical AND. We say the intersection of A and B. Let's take a look at the truth table. Let's use the child example again. Now the child's request is this: "Mom, get me vanilla and chocolate ice cream." Let's see the mother's options. If she doesn't buy either chocolate or vanilla, the child will be sad because the request wasn't fulfilled. If the mother buys a scoop of chocolate, the child won't be happy because they also asked for a vanilla. If she buys a scoop of vanilla, the child will still be disappointed because they wanted a chocolate too. In this case, the mother needs to buy both scoops to make the child happy. The intersection can also be seen as the product of two sets. Let's look at the example highlighted by the arrow. If A is false, 0, and B is true, 1, then the intersection of A and B is A times B, which will be 0. Think about the other cases as well. I would like to introduce you two identities in the topic of sets, which we are called De Morgan's identities. Let's take a look at the first one. It states that the complement of the union of A and B is equal to the intersection of the complements of A and B. What does this mean visually? Let's see. Let's define the sets A and B, which are the subsets of a universal set U. Form the union of A and B, and then take the complement of this union. This will be the complements of the union of A and B. Let's try to reproduce this from using the complements of A and B. Let's examine the two complements. We know that the complement of A is true, or 1, when we are outside of set A. It is false when we are inside. The same applies to the complement of B. Let's overlay the two complements. Now, let's look at the intersection of the complements. This means finding the part where both sets are true. Alternatively, we can say it is where the product of the two sets is 1. It is clear that in the intersection of A and B, neither is true. Within set A, the complement of B is true. Within set B, the complement of A is true. Outside of both sets, both are true. So we are looking for this. Let's compare it with the original form. It is evident that the same outer yellow set can be achieved within both operations. Therefore, these two operations are identical. The second De Morgan identity can be written in the following form. It states that the complement of the intersection of A and B is equal to the union of the complements of A and B. Let's see how this can be visualized. Let's define the set A and B, which are subsets of universal set U. Form the intersection of A and B and then take the complement of this intersection. This will be the complement of the intersection of A and B. Now let's create this using the complements of A and B. Let's examine the two complements. Overlay the two complements. Now, let's look at the union of the complements. This means finding the part where at least one of the sets is true. Alternatively, we can say it is where the sum of the two sets is 1. It is clear that in the intersection of A and B, neither is true. Within set A, the complement of B is true, and within set B, the complement of A is true. Outside of both sets, both are true. So, we are looking for where at least one is true. Let's compare it with the original form. It is evident that the same outer yellow set can be achieved within both operations. Therefore, these two operations are identical. I hope this video helped. If it did, leave a like and subscribe so we can keep learning together. I'm curious about your thoughts. Write a comment and let me know what topic would you like to see next. See you soon!